Okay, we're going to go through today and just look at some examples. And we're going to start off with an example that's similar to what we saw yesterday, or the previous video. So we have x double prime plus 4x prime plus 4x is 7e to the 8t. And we're going to start off exactly like last video and first look at the homogeneous solution. And the reason we're going to be doing this is that this is a constant coefficient. It's linear, it's higher order, and it's non-homogeneous because the right-hand side is not equal to 0. So for the homogeneous solution, we look at x double prime plus 4x prime plus 4x is equal to 0. Right, so we look at the case when the function on the right-hand side is 0. So now this is homogeneous. And this is the exact same thing we saw in the previous video. And in that video we showed that this solution looks like r1 e to the minus 2t plus r2, oops, let me be careful, r2t e to the minus 2t. Now for the particular solution, we go back and look at the differential equation. And we ignore the homogeneous part and focus on what happens to the solution when we have that. Now we are looking for a function, and we take the function, take derivatives, and add them up, we get an exponential. And so you should be thinking it should be something like e to the 8t, because when I take derivatives of this, I keep getting e to the 8t, and I'm going to hope that I can find a way to make everything canceled so that I end up with 7 of those things. So I don't know how to do that offhand, so I'm just going to call this ae to the 8t, and I'm going to plug it into the equation and see if that gives me enough information to get a. If not, I have to go back and do something different. All right. So I need the first derivative. That's going to be ae to the 8t times 8. And I'm going to need the second derivative, ae to the 8t times 8 squared. And I'm going to plug it back into my original equation. So the second derivative is 64 e to the 8t plus 4 times the first derivative. And the first derivative is 8a e to the 8t plus 4 times the function is 4a e to the 8t is 7e to the 8t. So I've got 64 a's, 32 a's, and 4 a's. So that becomes 64a plus 32a plus 4a. So this becomes what? 96 plus 4 is 100a. So the left-hand side is 100a. Is, oops, e to the 8t is 7e to the 8t, and I'm looking for an a that'll make this work. So that implies that 100a equals 7, or a equals 7 over 100. So now my solution then is the homogeneous plus the particular. And the homogeneous solution is r1 e to the minus 2t plus r2 t e to the minus 2t, and the particular is 7 over 100 e to the 8t. Now there was one thing I did not do here, and I should have been more careful. When I picked that for my particular solution, this is not e to the minus 2t. If that had been e to the minus 2t, I would know in advance that if I plug it into here, I'm going to get 0 because of that. So because it was not the same or had parts of my homogeneous solution, I knew I could just carry straight on and work from there. Let's look at what happens when my guess would have been that. So suppose now I had x double prime plus 4x prime plus 4x is 3e to the minus 2t. Okay, so the first thing is the homogeneous solution. And again, we already know that that's r1 e to the minus 2t plus r2 t e to the minus 2t. And now I'm going to look at the particular solution. And for the particular solution, the second derivative plus the first derivative plus 4 times the function should add up to 3e to the minus 2t. So I am looking for a function that when I take the function, take derivatives of it, I get e to the minus 2t. My guess should be e to the minus 2t. And that's because when I take derivatives of this, I'm going to end up with e to the minus 2t, and I know that that result should look like this exponential. The problem is this thing is part of my homogeneous solution. I already know that if I take this and plug it in, I'm going to get 0. So what do? Is we're going to amend this. We're going to multiply by t. So I take this part of the homogeneous solution, or this part of the particular solution, multiply by t, and then ask if that's going to be okay. But I got to, again, go back and check for my homogeneous solution. This thing is already part of the homogeneous solution. I already know that if I plug this into my equation, that I'm going to get 0. That's not going to work. So what do? I take that thing and I'm going to multiply by t again. That is going to be my next approximation or best estimate for the particular solution, but I still got to go back and check. That is not part of the homogeneous solution, so I'm confident that if I plug this in, I should not get 0. If I get 0, then I miss something in what I did the other day for getting that. So let's work with this. So what do we have? I'm going to take this and I'm going to plug it into my differential equation. So my differential equation looks like this. So I'm going to need to take the first and second derivatives, plug it into here, and hope I can make that work out. So let's rewrite this. So I have x double prime plus 4x prime plus 4x is 3e to the minus 2t. My guess for the particular solution is something times t squared e to the minus 2t. And I'm going to plug this into the equation and see if that can imply the value of a. Now to do this, I need to take two derivatives. I got to be careful. I have to use the product rule. Derivative of t squared is 2t plus a t squared. Derivative of e to the minus 2t is e to the minus 2t times minus 2. And now the second derivative. So derivative of 2t, so again I got to use the product rule here. Derivative of 2t is 2. So I get a2 e to the minus 2t plus a2t. Derivative of e to the minus 2t is e to the minus 2t times minus 2. And now I got to use the product rule on this. So derivative of t squared is 2t. And I got to bring this minus 2 for the ride. And then I'm going to have plus at squared. Derivative of e to the minus 2t is a to the 2t times minus 2. So I've got to square the minus 2. I'm going to plug this in. That's a bit of a mess. Let me clean this up. So let's see. That's 2a e to the minus 2t. For the 2t terms, I've got, this is a minus 4. That's a minus 4. So that becomes minus 8at e to the minus 2t when I add those two together. And then when I expand this out, minus 2 squared becomes 4. So I get 4at squared e to the minus 2t. So I'm going to take this and plug it into the original equation. Second derivative is 2a e e to the minus 2t minus 8at e to the minus 2t plus 4a t squared e to the minus 2t plus 4 times the first derivative, so this becomes 2at e to the minus 2t, and then bringing that minus 2 to the front, I get minus 2a t squared e to the minus 2t, and then I'm going to have plus 4 times x, so I get 4a t squared e to the minus 2t, and all that is 3e to the minus 2t. Alright, that's still a lot. Let's do the algebra. Notice I'm doing this step by step. I'm trying not to skip steps because there's a lot to keep track of and it's going to be a mess. So this becomes 2a e to the minus 2t minus 8a t e to the minus 2t plus 4a t squared e to the minus 2t. All I did was rewrite this term. I'm going to multiply through by the 4. So this becomes plus 8a t e to the minus 2t minus 8a t squared e to the minus 2t. And I'm going to add this term, so 4a t squared e to the minus 2t. This all has to add up to 3e to the minus 2t. Notice this becomes 2a e to the minus 2t. Minus 8 of these plus 8 of these gives me 0. 4 minus 8 plus 4 of these gives me 0. So I need to find a value of a that makes these two things equal. So e to the minus 2t is never 0, so I can divide that out. So I get 2a equals 3, or a equals 3/2. So my solution then is the homogeneous, which we said before was r1 e to the minus 2t plus r2t e to the minus 2t plus the particular solution, which we said was a, which is 3/2 times t squared e to the minus 2t. And I can go back in and plug this in and check to see if it works. But I just want to note that we had a couple checks on the way. All the t squared and t terms canceled. And if they had not canceled, that means I had done something wrong. Either my homogeneous solution was wrong, or my guess was bad, or I did a calculus or algebra mistake somewhere. So the fact that we ended up with just an e to the minus 2t on the left and right was a quick check that should have made us feel good about how things are going. All right, let's look at another example. Let's look at x double prime plus 16x equals 14 e to the 2t plus 5t squared. First step is to look at the homogeneous solution. So x double prime plus 16x is 0. Right? And the reason I'm doing this is constant coefficient, it's linear, and it's not homogeneous. So for the homogeneous part, I just set everything on the right equal to 0. I'm just going to blindly try an exponential function, and if it works, it works. I'm going to plug it in, so I need to take two derivatives. So I get re to the nt times n for the first derivative, and for the second derivative, I get re to the nt times n squared. I plug it into my homogeneous solution. So the second derivative is re to the nt times n squared plus 16 times the function. So I get 16 re to the nt is 0. Notice there's an re to the nt in everything. So I can factor that, leaving me with an n squared plus 16. That cannot be 0 because that's my solution. So I get n squared plus 16 is 0. N squared is minus 16. So n is plus or minus the square root of minus 16, which is plus or minus 4 times I. So my solution then looks like r1 e to the 4it plus R2 e to the minus 4it. And notice there is 0 real part. So this means I can write this as e to the 0t for the real part times c1, and then for the imaginary part is 4. So I get c1 cosine 4t plus c2 sine of 4t. And e to the 0 is 1, so this is just c1 cosine of 4t plus c2 sine of 4t. And again, I can take two derivatives of this, plug it in, and see that it works. I'm not going to do that for time constraints, but you should be aware of that. So now, what do we have? We have our particular solution. So our original equation looked like this, and our homogeneous solution is c1 cosine of 4t plus c2 sine of 4t. For my particular solution, so this is the second step, I ignore the homogeneous solution. So I have x double prime plus 16x is this mess. And I'm going to divide and conquer. I have an exponential and I have a polynomial, so I'm going to treat those two things separately. For the exponential, I'm looking for a function. So when I take the function, take derivatives of it, and add it up, I get e to the 2t. So I don't know what e to the t function is going to give that to me, so I just call that a times e to the 2t. I'm going to plug it into the equation and ask what does that assume about a. For this part of it, I've got a polynomial. It's a polynomial of degree 2. So what kind of function, when I take it and take its derivatives, gives me a polynomial of degree 2? Well, it's going to be another polynomial of degree 2. Again, I don't know which polynomial of degree 2 is going to work. So let me just call it a general second order polynomial, bt squared plus ct plus d. This is going to be used to take care of this. The exponential is being used to take care of that. So my guess is going to be something in this form. And I'm going to take the first and second derivatives, plug it into this equation, and see if that is enough information to determine what a, b, c, and d are. So the first derivative is going to be a e to the 2t times 2, because the derivative of 2t is 2. Derivative of t squared is 2, so that becomes 2bt. Derivative of c times t is c, and derivative of d is 0. Okay, we're assuming a, b, c, and d are all constants. Second derivative. Derivative of e to the 2t is e to the 2t times 2. And since I already have a 2 there, that becomes 2 squared. Derivative of 2bt is 2b. Derivative of c is 0. So now I'm going to plug it into my equation. So the second derivative is 4a e to the 2t from this term, plus 2b from here. And I'm going to take 16. Oops, I got to be careful. Not sure why I put an x prime there. 16 times x. It was correct in the first page. Sorry. 16 times x becomes a e to the 2t plus bt squared plus ct plus d. And this, in the end, should all equal 14 e to the 2t plus 5t squared. And I should note, if this is a general polynomial of degree 2, I can think of this as 5t squared plus 0t plus 0. That is my polynomial of degree 2 that I'm working with. So let's do the algebra, expand all that out. So I get 4a e to the 2t plus 2b. Multiplying through by the 16, I get 16a e to the 2t plus 16b t squared plus 16ct plus 16d. And that has to be 14 e to the 2t plus 5t squared plus 0t plus 0. All right, so I've got that. oops, I'm going to be careful, plus that. Those are my exponential terms. So 14a e to the 2t plus 16a to the 2t adds up to 20a e to the 2t. This is my only t squared term. For my t term, this is my only t term. And then for my constant term, oops, I gotta be careful. This should just be 16d. Sorry. For my constant term, I have 2b plus 16d. And all of this has to be 14e to the 2t plus 5t squared plus 0t plus 0. If the function on the left is equal to the function on the right for all t, then the exponential terms have to match up and be the same. Right? So that means that 20a e to the 2t has to be 14 e to the 2t. Likewise, the t squared terms have to match and be the same, which means that 16b t squared equals 5t squared. And the linear terms have to be the same, which means that 16ct is 0t. And lastly, the constant terms have to be the same, so that means that 2b plus 16d is 0. All right, let's rewrite that. That's a lot. So what did we have? We had our differential equation, which is x double prime plus 16x is 14e to the 2t plus 5t squared. We had a homogeneous solution of c1 cosine 4t plus c2 sine of 4t. Now for my particular solution, I guessed a e to the 2t plus bt squared plus ct plus d. And note, none of these terms look like cosine 4t or sine 4t. So I could just went ahead and plugged in, and I got the following equations. 20a e to the 2t is 14e to the 2t. 16bt squared is 5t squared. 16ct is 0t. And 2b plus 16d is 0. So basically at this point I just stop and reset and think about, what does this mean? E to the 2t is never 0. The only way this can be true is if 20a equals 14 or a equals 14 20ths. This has to be true for all time, not just t equals 0 or t equals 1 or whatever, all values of time. And that can only be true is if 16b equals 5 or b equals 5/16. Okay. This also has to be true for all time, no matter what the time is. If t is 0, 1, 2, 3.5, square root of 5, whatever, that has to be true. And that's only going to be true if 16c is 0, which implies that c is 0. And now here, I got to solve for b and d. But note, I already know b. I don't know d. All right, so I know that b is 5/16. So this says that 16d is minus 2b. Or d, if I divide both sides by 16, I get minus 2 over 16b. Minus 2 over 16 becomes minus 1/8. b is 5/16. So this becomes minus 5 over 8 times 16. And it's going to be 64 times 2 is minus 5 over 128. So my solution then is the homogeneous plus the particular. Homogeneous solution is c1 cosine of 2t plus c2 sine of 2t plus, now the particular, a is 14/20 e to the 2t plus b is 5/16 t squared. C is 0, so 0 times t, and then d is minus 5 over 128. Okay. And I could go through and check it, plug it back into the equation, and see what happens. But because of interest and time, I'm not going to do that. It's important to note that was a really long and tedious process. Unfortunately, it's a lot. So notice it's really important for you to move carefully and to be organized and do one step at a time. If you try to take too many steps at one time and you have to go back, it becomes very difficult to find that. You notice I made a couple mistakes because I was just doing one step at a time. I could go back and look at my past work and more easily find the source of the mistake. If you take 2 steps at a time and you go back to try to find a problem, it'll be nearly impossible. So being careful, moving more slowly will actually help you solve these things more quickly. Okay. All right, next example. Suppose I have x double prime plus 16x is 3 sine of 4t. We already know that the homogeneous solution is c1 cosine of 4t plus c2 sine of 4t. For the particular solution, my particular solution is going to satisfy xp double prime plus 16xp prime, 16xp is 3 sine of 4t. Okay, I am looking for a function. I take the function, I take derivatives of it, and add things together, I'm going to only be left with sine. You should be thinking sine, because when you take derivatives of that, you're going to get sine. But if you take an odd number of derivatives, you're going to get a cosine. So you should include a cosine in there just in case, because you do not know in advance that that's going to pop up. So I'm going to use a times sine of 4t plus b times cosine of 4t. That's going to be my guess. I'm going to plug that into the equation and see what happens. Now, I'm going to go through and do this, and in this particular case, it's going to turn out that I didn't need the b. Be very careful in that there are circumstances when you do need that, right? It just happens that in this example, I chose this example because it's going to be slightly less tedious. And you'll see that this becomes a huge mess, and I'm going to be very careful. I can come up with situations where you do need the cosine if you forget the sine. So just be warned that as I go through this example, it's going to seem like I don't need this, but in general, I often do. All right, so there's my particular solution. Now, before I start plugging this in to see what happens, I should already note this is not going to work. I already know if I plug in sine of 4t or cosine of 4t, it's just going to add up to 0. So I have to take this whole thing and multiply by t. So that means my particular solution, my guess, is going to look like at sine of 4t plus bt cosine of 4t. And I'm going to take derivatives of this and plug it in. And because of the product rule, I know I'm going to end up with terms that look like t times sine and t times cosine. If those do not cancel out, that means I made a mistake somewhere. Okay. In the end, I should only end up with cosines and sines. And I'm going to have to use the product rule here. So I'm going to have to stay organized and go through this. And this is, again, it's just going to be an awful lot. And I'm going to make mistakes. You're going to make mistakes. That's just unfortunately, part of being human. Just be very careful, and as you go from steps to step, go back and look at things, and just know that when I do this, I look at it and I go back and I take a glance at the previous and ask, does it make sense? And I'm not necessarily saying it out loud, just because out of habit I do that. And you should get into that habit where you go back and check your work. Every time you take a step, look at the previous thing, ask, does it even make sense? And then ask, is it correct? All right, let's start over here, because again, this is going to be a mess and I'm going to need room. So my particular solution, satisfies xp double prime plus 16xp is 3 sine of 4t. I made a guess that my solution looks like at sine of 4t plus bt cosine of 4t. I'm going to take that and plug into my equation, and I'm going to ask, does that give me enough information to figure out the values of a and b? And at the end of the day, I should have 2 equations, 2 unknowns. Because my unknowns are a and b, I'm going to need 2 equations. So let's take the first derivative. I need the product rule. So derivative of t is 1. So I get a sine of 4t. And then the derivative of sine of 4t is going to be cosine of 4t times the derivative of 4t, which is 4. Now for the derivative of the second term. Derivative of t is 1. So I'm going to get b cosine of 4t. Now I'm going to take bt times the derivative of cosine. That's going to be minus sine of 4t. The derivative of 4t is 4. All right, and now I need a second derivative because I'm going to plug that in. Derivative of a sine 4t is a cosine 4t times 4. Derivative of at cosine 4t times 4. Well, derivative of at is just a. So I'm going to get a cosine of 4t times 4. Derivative of derivative of cosine of 4t for the next term, I'm going to have at times minus sine of 4t times 4. And I got to bring down the times 4. Okay. Derivative of b cosine 4t is going to be b times minus sine 4t times 4. Now I've got to use the product rule here. Derivative of bt is b. This is going to stay the same as minus sine 4t times 4. And now derivative of minus sine 4t, so I got plus bt is going to be minus cosine of 4t. Derivative of 4t is 4. So I'm going to get a 4 squared. Okay. Let me clean this up. And again, I can't emphasize enough. I'm doing this term by term, step by step. I'm not combining steps. I have 4a cosine 4t plus 4a cosine 4t is 8a cosine 4t. This becomes, so 4 times 4 is 16 minus, so I get minus 16a t sine of 4t. For this term, I have minus 4b sine 4t minus 4b sine t gives me a total of minus 8b sine 4t. And this term becomes 16 times minus, so I get minus 16 bt cosine 4t. Okay. So now I'm going to take my second derivative, first derivative, and function and plug it into my non-homogeneous equation. Second derivative, I get 8a cosine 4t minus 16 at sine of 4t minus 8b sine of 4t minus 16 bt cosine of 4t plus 16 times my function, and that's going to be at sine of 4t plus bt cosine of 4t is all equal to 3 sine of 4t, which is coming from there. All right, I'm going to multiply this 16 through. So I get 8a cosine 4t minus 16 at sine of 4t minus 8b sine of 4t minus 16 bt cosine of 4t. Multiplying through by the 16, I get plus 16 at sine of 4t plus, now this becomes a 16 bt cosine of 4t is all equal to 3 sine 4t from my right hand side. Now I should immediately notice nice things happening. Minus 16 plus 16 of these gives me 0, and minus 16 plus 16 of these gives me 0. So those cancel. So what am I left with? I'm left with this term. So I get 8a cosine of 4t minus 8b sine of 4t has to be equal to 3 sine 4t. Now, in my original equation, it just looked like that by itself. But I have a cosine over here, so I can think of this as being plus 0 times cosine. And the reason I'm doing that is I have to match coefficients. The only way the thing on the left can be equal to the thing on the right is if the sine terms are equal and the cosine terms are equal. Those have to be able to cancel out. So let me rewrite that. So at this point, what do I have? I have 8a cosine 4t minus 8b sine 4t is 3 sine 4t plus 0 cosine 4t. The sine terms have to match, so this is minus 8b equals 3. The cosine terms have to match, which says that 8a is 0. This says a is 0. This says b is minus 3/8. Okay, so that means my particular solution is going to be, so I originally said a sine 4t, so that's going to be 0 sine of 4t, and then oops, that's wrong. My original guess then was at sine of 4t plus bt cosine of 4t. And I just showed that a is 0. And then b is minus 3/8. Like so. So that means my solution is x homogeneous plus x particular. My homogeneous was C1 cosine 4t plus C2 sine of 4t. Now my particular is minus 3/8 cosine 4t. Just a quick notice. If you had originally just guessed sine because there was a sine on the right-hand side, you would have had a problem in that this term actually mattered. Vice versa, if you had just guessed cosine without the sine, again, I can come up with examples where that will give you problems. So it's absolutely vital that you include all possible terms that could come about when you start taking derivatives. All right. Let's do some more examples. So in this example, I have x double prime plus 3x prime is 5 plus t e to the 7t. its constant coefficient, it's higher order, it's linear, and it's non-homogeneous. So I'm going to first look at the homogeneous solution, which is x double prime plus 3x prime is 0. I'm going to guess an exponential, which means now I'm going to take the first derivative, so I get re to the nt times n. Take the second derivative, get re to the nt times n squared, plug it in to here, to my homogeneous equation. So I get re to the nt n squared plus 3 times the derivative, which is 3e to the rnt equals 0. The whole thing is 0. I can factor out re to the nt, and I'm left with n squared, plus 3n is 0. I don't want r to be 0, because that would mean my x homogeneous is 0. So that means that n squared plus 3n is 0. Let's factor out an n. So n is 0, or n is minus 3. So my homogeneous solution is r1 e to the 0t plus r2 e to the minus 3t. So that means I get r1 plus r2 e to the minus 3t. All right. Now for my particular equation, I have x double prime plus 3x prime equals 5 plus t e to the 7t. I'm going to do divide and conquer. I basically have a polynomial plus some ugly exponential thingy. Focusing on just the polynomial, it's a polynomial of degree 0. So if I'm looking for a function and I'm taking derivatives and I plug it into the equation and add things up and I get a polynomial of degree 0, I should just guess a polynomial of degree 0. Problem is, there's a polynomial of degree 0 in the homogeneous solution. So that is not going to work. I know if I plug in a constant into my original equation, if I start taking derivatives of this, it's just going to give me 0, because that's the homogeneous solution. So I have to multiply the whole thing by t. All right, now for this other term, I am looking for something that when I take its derivative and take multiple derivatives and add things up, I'm going to get something that looks like a polynomial of degree 1 times an exponential. So my guess should be a polynomial of degree 1 times an exponential. Because when I use the product rule and take derivatives of that, I'm going to keep getting polynomials of degree 1 times an exponential. I don't know what that polynomial of degree 1 is going to be, but I do know the exponential has to be e to the 7t. Because when I take derivatives of that, I'm just going to get e to the 7t. So the most general polynomial of degree 1 is just going to be something times t plus a constant. Oops, and this should be my particular solution. So for my particular solution, and I got to be careful, this does not coincide with my homogeneous solution. Right? There's not an e to the 7t anywhere. So if there were, I would multiply the whole thing by t. But since there's not, I'm going to stop here. So my guess for my particular solution is this. I'm going to try that out. I'm going to plug this into my equation, and if it works, it works. If it doesn't, I'm just going to try something else. Especially when you first do this, you make mistakes. It's just part of the process. And I can't say other than I have a feel for this, and I've screwed this up before. When I first started doing this, I would have just said BT and left out the C. And you've got to make those mistakes and grow from it. So what's really important is try something, recognize whether or not it works, and if it doesn't work, ask, why did that not work, and what could I have done better? And you absolutely have to do this and try this and work it out. watching me go through and do this and magically come up with that is not going to help you. This is not going to help you. So where are we now? We have our homogeneous solution is going to satisfy this equation, and we think, and we may be wrong, that our solution, for the particular solution, looks like AT then plus BT plus C times e to the 17. And I'm going to hope it works. I'm going to plug it into the equation and see if that gives me equations for A, B, and C. And by the way, I have 3 equations. I know in advance, I know now that I'm going to need 3 equations. So I'm going to need to plug it into the equation. I'm going to need to take 2 derivatives. Derivative of AT is A. I have to use the product rule here, so the derivative of BT plus C is just B. And then I'm going to have plus BT plus C. Derivative of e to the 7t is e to the 7t times 7. And now I need a second derivative. Derivative of A is 0. Derivative of B, e to the 7t is b e to the 7t times 7. I'm going to need the product rule here. Derivative of BT plus C is B. The rest of the stuff just comes along. And then I'm going to have BT plus C. Derivative of e to the 7t is e to the 7t times 7. But I've already got a 7 there, so it's 7 squared. All right, let me just go with this. Let's see why, but this is, again, this is a mess. I'm going to plug this into this equation. So the second derivative, I have 7b e to the 7t is this expression. Why does that look wrong? Oh, that's right. Okay. Plus, this becomes 7b e to the 7t. And so, by the way, notice I didn't like that, how it looked, and I went back in, recognized that this came from the product rule. That was bad writing. So this is 7t. So that took care of this term, and now this term becomes 7 squared, or 49, bt plus c e to the 7t. That's my xp double prime, plus 3 times xp. So 3 times this term is at plus the quantity bt plus c times e to the 7t. All has to add up to 5 plus t e to the 7t. Okay, what a mess. I'm going to basically expand everything out as far as I can, then collect like terms, and then ask, how can I get the thing on the left equal to this? And I'm going to basically ask that all of the coefficients on like terms match up. So notice here, this plus this, 7 b's of these plus 7 b's of these is going to be 14b e to the 7t. Takes care of u and u. I'm going to multiply this through, so I'm going to get 49 bt e to the 7t plus 49 c e to the 7t. So I've expanded this out as far as I can. Now multiplying this 3 through, I'm going to get 3a. This is going to be 3 times bt times e to the 7t. This is going to be 3c e to the 7t, all equals, and I'm going to leave the right-hand side alone, 5 plus t e to the 7t. So 14, 49, 49, 3a, 3bt plus 3c. Do I have any like terms? So I have b e to the 7t, c e to the 7t, and 3c e to the 7t. And actually, let me stay consistent with that, because I have a constant term there. This is my only constant term. Let me write that first. 3a. Then for my e to the 7t terms, I've got 14b from there. This is plus 49c. And this is plus 3c. So that takes care of all my constant terms, all of my exponential terms. And then for my terms that look like t e to the 7t, I've got 1 there, so that's 49b. And I've got 1 there, and that's 3b. All of that adds up to 5 plus t e to the 7t. Okay. Now, what does this imply? The only way the left-hand side can be equal to the right-hand side is if the constant terms are the same. So that says that 3a equals 5. The e to the 7t terms have to be the same. Notice on the right-hand side I don't see it, so that means there's really 0 of these things. So all of these things, so let's see, 49c plus 3c is 52c, have to add up to 0. And then all of the te to the 7t terms have to add up to 1. So this is 49 plus 3. It says 52b has to equal to 1. And I have 3 equations, 3 unknowns. Hopefully that's enough. So now I just stop and reset and stop to think, how do I solve a system of equations? So I'm going to pull out that part of my background. I'm going to do this one first because that's easiest. 3a equals 5 implies that a is 5/3. This is the next easiest one. 52b is 1, which implies that b is 1 over 52. And so now it leaves the one hard one. So I have 14b. b is 1 over 52 plus 52c is 0. I'm after the c. So let me subtract 14 over 52 from both sides. So c is minus 14 over 52 squared. So I have A, B, and C. There's no ambiguity here. There's nothing missing. So that means my estimate might have been okay. If these things had been inconsistent or there had been missing pieces, that means there was probably an issue somewhere. Bad guess, bad calculus, or bad algebra. Just because this is consistent now doesn't mean I did everything right. It's possible, very possible I made a mistake somewhere. So what did we have? We had our original equation was x double prime plus 3x prime is 5 plus t e to the 7t. Our homogeneous equation, I gotta go back and look, we said was r1 plus r2 e to the minus 3t. So again, you got to be really careful here. And we just decided that our particular solution, so I'm coming back to here, was a times t plus the quantity bt plus c e to the 7t. A, we decided, oops, where did I put that? Oh, put it back here, was 5/3. So that's 5/3 t. B we decided was 1 over 52. And C was minus 14 over quantity 52 squared. And all that times e to the 7t. So my solution now is the homogeneous, which is r1 plus r2 e to the minus 3t, plus the particular. And I'm just going to rewrite that. That's times t e to the 7t. Oh, man. What a lot of mess. Okay. All right. I'm just going to, so that was a whole lot. I'm going to go through and look at some things and just talk about how I would guess homogeneous solutions. I'm just going to look at this previous example. So in my previous example, or in this example, what did I have? I had x double prime plus 3x prime is t e to the minus, sorry, this is my next example. In my previous example, I had something similar to this, but I found that the homogeneous solution was R1 plus R2 e to the minus 3t. If I were to guess a particular solution, because of this, I would guess bt plus c e to the minus 3t. Right, because I have a polynomial of degree 1, and this is a general polynomial of degree 1 times the exponential. Notice this coincides with that, so I have to multiply the whole thing by t, which means that my particular solution that I'm going to guess looks like that. If I had x double prime plus 3x prime is t squared e to the minus 3t, again, my homogeneous solution looks like that. My guess, so I have a polynomial of degree 2 there, so I should guess a polynomial of degree 2 times e to the minus 3t. So that would be at squared plus bt plus c. However, that, bt, I gotta be careful, this right here corresponds to that. Because this times this is matching that, I have to multiply the whole thing by t. So my guess would be at cubed plus bt squared plus ct times e to the minus 3t. If I had this differential equation, so the same thing, but let's suppose it's plus cosine of 8t. My homogeneous solution is R1 plus R2 e to the minus 3t. My guess, I'm going to break it up into two pieces. For this part, just as I said before, should be a polynomial of degree 2 times e to the minus 3t. For this part, I should guess A cosine 8t plus B sine of 8t, because when I take derivatives of that, I'm going to get cosines and sines, and I'm going to hope it's possible to get those things to cancel. Now when I go back to look at the homogeneous solution, I look at these two things separately. This thing right here has a match with my homogeneous solution, so I need to multiply that by t. This part does not have a match, so I leave it alone. And so now this becomes my guess that I'm going to try and plug back into the original equation and work it out. And as you can see, this would be a horrific mess and horribly boring to watch me do. I'm going to leave it at that. The key thing when you're working these problems, recognize what you have. Recognize that it's constant coefficient, it's linear, and non-homogeneous. Solve the homogeneous part first. Make a very general guess that's going to take care of the kinds of functions you have on the right, and you make your guess as general as possible. You're going to plug it into the original DE and see if you can make things cancel. Knowing that, if you have something that looks like the homogeneous solution, you already know it's going to add up to 0 and it's not going to work. So for each piece that's designed to tick off a kind of solution, if that piece corresponds to your homogeneous solution, you multiply the whole thing by t and then treat the other parts separately.